Okay, I'm going to take you through a collection of functions that I really think you should know what the graph looks like in general. You might not be able to look at them and graph them perfectly, but you should have a general idea of the slope, and then you should be able to plot a couple points. So let's just start you out with some linear function. So anytime we start talking about a thing that's in the form y equals mx plus b, you know that's just some line. Special things about lines is they have an x-intercept, a y-intercept, they have a constant slope, and in this form you know that this is the y-intercept and this is the slope, and you have some linear function. Okay, then you can come over here to some quadratic, and typically our quadratics are of the form ax squared plus bx plus c. You know that if it's a positive quadratic it might look something like this. If it's a negative quadratic, it's going to be a frown. Plus c is still the y-intercept, and so on. This one wouldn't have any x-intercepts, which would be fine. You could use the quadratic formula to find those. In this case, you'd get imaginary numbers. But in general, you know that a quadratic looks like that. And a quadratic does have symmetry about its vertex. Okay, in this case, the quadratic would have a minimum value, and then the maximum is just all the way to infinity. So then this is our cubic. A positive cubic function would look something like this. If you graph this on the calculator, you would see that it has a 0 at -2, 0, and 4. And so it's going to have some sort of general shape like this. And so it increases and then decreases and then increases. In this case, it has 3 different roots. It doesn't have to. It could just have one. It could just go through and then hump up there. This one happens to have 3, and it's a cubic. A positive cubic looks like this. A negative cubic is going to look, it's going to come down and go up and then go down. Okay, this is our typical rational function. Okay, as you approach 0, it's going to get up to infinity. It's going to have a horizontal asymptote. And then down here, it's going to look like that. That's our typical rational expression. Our square root graph kind of tails off. This one has a domain that starts at 4. I've shifted it to the right, and it does something like that. And again, that's our typical square root curve. This x minus 4 is a shift. It wouldn't matter if I put a -4 there or a -4 there, or if you factor this and it was an x minus 4 something squared. All of those things are just horizontal shifts when they're inside of the function. So in this case, you moved it to the right, and it's this general shape. If there was a minus sign out here, it would flip down. If there was a minus sign in there, it'd flip the other way. So we can all talk about what those things do. This is your absolute value graph. This is going to increase the slope to 2, and this is going to move it up to 3. So when we start here, we're going to go like this. It's going to look like our V, and it is going to start at the point 0, 3, and it's going to go up with a slope of 2. So that's kind of how those things affect. X to the 2/3 power, well, x squared looks like this, except then you're going to take the cube root. So this is a little bit less than linear, and so it's going to bend. So it's going to bend like this and bend like that. So that's what x to the 2/3 looks like. Now x to the 1/3 looks like a cube root. Okay, now so when you get this over here, you can think of this as x squared to the cube root. So you can see that the graph is always positive because you're always squaring it. Here there's no squared, it's just the cube root. So it's going to bend and then also bend negative numbers, because you can put in negative numbers here and just be fine. You can put in negative numbers here. The domain is everything, but the range is only going to be positive numbers. And over here, the cube root of -8 is -2. So that's what a cube root would look like. No range or domain restrictions. Okay, here's our typical sine function, except it's a -3. The 3 is going to be the amplitude, and the negative is going to make it go down first, and then up. So it would look something like that, where this is going to go up to 3 and down to -3, and it happens to go down first because of the negative sign. Our cosine curve is going to start up here, and I'm going to draw this one a little faster than normal. That's what that 2 is going to do. It's going to increase the period. All right, multiplying this by 2 is going to make it twice as fast. So the old period was 2 pi, and this period would only be pi. Just as a reminder, the period, we would use a capital T, and it is 2 pi divided by omega, where this number here is omega. I know it looks like a W, but it's an omega. So in this case, if we wanted to figure out the period, normally, like the period of a normal function with no adjustment, well, that's just, omega is just a 1, and so the period is just 2 pi over 1, which is 2 pi. So if this is a 2, we'd get a period of pi, which means the period is half as long because it oscillates twice as fast. Tangent, we have asymptotes. All right, and those asymptotes are at pi over 2 and negative pi over 2. The period of tangent is pi, as you can see, and then it just keeps doing that over and over. So you can just repeat, keep drawing that. We have our logarithm. Our logarithm looks like this. It's super slow. It gets really, 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 really flat. This value is 1, 0, because the logarithm of 1 is 0. You could plot other points on here. If you plotted this point, this would be e, 1, right? The natural log of e is 1. So we could plot points, but then we do have this vertical asymptote at x equals 0. Okay, kind of go through this list before I kind of flip it over, but we have linear, quadratic, cubic. These are our polynomial graphs. And again, you can make the power as much as you want. If you look at x to the 4th, it kind of looks like a w, or negative x to the 4th looks like an m. Square root, cube root, 2/3, these are all roots. They all kind of bend. They're less than linear. Square root has some domain restrictions on them. This has got no domain and no domain. This, you're squaring it, so this one's always positive. As you can see, it's always up. Absolute value, we shifted it up and we made it a little steeper. This is our typical rational function where we have a vertical and a horizontal asymptote. And then we have sines, cosines, and tangents. Tangents have a period of pi. Cosines and sines have a period of 2 pi unless we make them faster, or we could have made them slower. I made this a negative, so it went down, and I increased this one to have an amplitude of 3. This went all the way up to 3 and all the way down to negative 3. This one would just oscillate between 1 and negative 1. Again, look at these graphs. You should be comfortable thinking about the domain, the range. You should talk about the slope. Here, this is a constant slope, some slope, and then the opposite slope over there. This slope is changing, certainly a changing slope. This slope, you can always see, this slope is always negative. This slope is always positive. The slope goes from positive to negative to positive to negative. So all sorts of things when we start looking at the slopes of these graphs. And then I thought I would throw these 5 extra ones. And so this is our rational expression, except what do these numbers do? The 4 doesn't really do much. The 2 shifts up our horizontal asymptote because this is going to go to 0, and 0 plus 2 is 2. And this moves our vertical asymptote over to 3. But then we still do have our typical function. And when if x is 0, this is less than 2, so it's going to be like there. And it's going to look something like that. Okay, this is our exponential curve. Way up, really, 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 really steep. And this horizontally asymptotically approaches 0. That is the point 0, 1 on this graph. And again, that's our classic exponential. This could be an e, this could be a 2, this could be a 5, and the graph would look very similar. This is going to be an exponential. This is going to shift everything up 3. So let's put a horizontal asymptote at 3. And when you let x equal 0, you're going to get 4. So it's going to go, but it's going to go this way this time because it's backwards. Oops. Something like that. So it's a decaying one, which is just the horizontal flip of this. Okay, that's not the best graph I've ever drawn, but you kind of get the point that it's going to decay this way, and it's going to decay. This is going to decay to 0, so 0 plus 3 gets a horizontal asymptote of 3. Okay, and I just wanted to draw these kind of in detail. You should know these very well. So there's our sine. Period is 2 pi. That's pi. Sine of pi is 0. Sine of pi over 2 is 1. Sine of 3 halves pi is negative 1, and then you should know all those values. Sine of 0 is 0. Cosine looks like this. Right, cosine of 0 is 1. Cosine of 2 pi is 1. Cosine of pi is negative 1. Cosine of pi over 2 is 0. And cosine of 3 pi over 2 is 0. So remember, you are thinking of sine as y values, right? Heights. Cosines you're thinking of x values of some angle. And again, if you're straight up, you have all the y value you can have. If you're straight down, meaning on the graphs, right, we're talking about this being pi over 2, pi, 3 pi over 2, back to 2 pi, right? If this is a y value, you start out over here, and as you rotate along the unit circle, right, you have no height. Straight up is all your height. Straight this way is no height. Straight down is -1. And then straight back to the right is then back to 0. Where cosine is an x value. You start having all this x, and then you get no x, and you get negative x. Right, we're there. Negative x, no x, back to there, and then all the way back to your one value of x. Again, you should know these graphs very well that you can start thinking about not only the graphs, their bounds, their domains, but you should be able to identify sine of 0 is 0, cosine of 0 is 1, things of that nature, so you don't mess up. Okay, so look back on all these graphs. On the back I kind of gave you some exponentials, and then I kind of reviewed a more complex rational expression, and then I looked in detail at the sines and cosines. And then again, review, you should be very comfortable with polynomials, rational expressions, cube roots, square roots, absolute values, sines, cosines, and tangents, and of course logarithms. Okay, so hopefully this helps give you kind of a general shape of the typical graphs that you will use in AP Calculus.